Hi, my name is Lucian, and today I will talk to you about pathfinding. First, a little introduction about me. I was also a student in the Olympiads. My best results were silver medal with 28 points at IMO 2007 in Vietnam and gold medal with 40 points at BMO 2007 in Greece. After I graduated, I continued to be involved in preparing the Romanian team and in 2018 I was a coordinator, and in 2019 and 2020 I was an observer for the Romanian team. Except mathematics, I'm also a software engineer, and this is why maybe this presentation is a bit heavy on computer science. I apologize for that. I tried to keep it more math oriented, but in my opinion, this theoretical aspect of computer science is very similar to combinatorics, as we will see. Ideas, at least some ideas, are shared. So I hope that you will enjoy it. So let's see what this is all about.
I will start this presentation with a small clip of me playing Dota 2. I control the helicopter unit and I want to reach the gold coin at the mouse position, which is labeled bounty. So for this, I'm going to click there and let's see what happens. Notice how the unit avoids all the obstacles in the path, and in the end it reaches the destination, and it does so in an optimal way. So, what I want to talk to you today about is pathfinding. And how do we make this happen? Let's begin with the statement of the problem. Consider 2 points in a plane, and also consider a set of polygons, which represent the obstacles. What we want to find is a short path between the 2 points that doesn't intersect the polygons. Notice how I use the word short and not shortest. That is because most of the times a short enough path is good, because the trade-off in computational time and power in order to determine the actual shortest path is not worth it. For example, if the shortest path is just 1% better than the one we found, but it takes us 100 times more time to find it, that's not really a good trade-off. So that's why I mention short. How do we prove it? So the first idea is something that I'm sure you've seen or even used in Olympiad problems. It's a bit of a classic. We're gonna use graph theory. So there are 3 main parts of the solution. First is to determine pathfinding in a graph. This is a well-known computer science challenge, so I'm going to explain a bit about how that works. Now, the more interesting part is what is the graph that we're talking about, because we have a configuration in the plane with points. So the idea is that we will construct a graph using a triangulation that is carefully selected. Then the triangles will become the vertices of the graph, and 2 triangles will be connected if they share an edge between themselves. The final part is just putting it all together and smoothing out the path. The first part is about the shortest path in a graph. So, what do we want to accomplish? Let's start with a connected finite graph and assign a cost to each edge. This means that we assign a positive number to each edge. This can correspond to distance or time or a combination. So what do we want to do? Given 2 points, we want to find the shortest path between these 2 points when looking at the cost. So the cost of the path is the sum of the cost of its edges. So first observation, it exists because there is a finite number of paths, so we can just take the minimal one. But in practice, can we do this? I mean, can we look at all the paths and compare them and take the minimal one? Maybe not. So let's look at a simple example, such as this graph in the picture, where you have a start point, an end point, and then there are 2 rows, one at the top, one at the bottom. The top row labeled by AIs and the bottom row by BIs. And note that vertex of index I is connected to a vertex of index I plus 1, both with A's and with B's. The graph here is oriented, just for an easier example. So how does a path look in this graph? It will be, start is S, of course, and then it will be a point with index 1, then a point with index 2, and so on, then a point with index n. In the picture, n is 5. So this is how a path looks like. How many paths are there? Well, at each step, we have two choices. We either pick the AI or the BI. So in total, we have 2 to the power of n paths. How long does that take on a computer? Let's assume that one path can be calculated and added up in about 1 nanosecond. This might be off by a factor of 10 or even 100, but it doesn't matter, as you'll see later. When we look at n equals 5, this is going to be really fast. So even if I'm off by a factor of 100, it's still way less than 1 second to do all the calculations. That's pretty good. But what happens if n is 100? Then we have 2 to the power of 100 paths. That's about 10 to the power of 30. And then when you start to count how many seconds are in a year, and then how many nanoseconds are in a year, and the number of paths is that big number on the screen, you're going to end up with about 10 trillion years for a computer to finish checking all the paths. Clearly, that's not going to work. So, we need to find a better way to deal with these paths. What if we pick the minimal edge at every step? This is also not going to work because there is an easy counterexample, such as the one that I put on the screen, where SA1 is, let's say, 10, SB1 is 20, so slightly larger, but then the A1, A2, and A1, B2 are very expensive, are 10,000, and all other edges are 1. So what happens now is that if I pick SA1 at the first step, because SA1 is the least expensive of the two edges, then the path is going to cost over 10,000. Whereas if I pick B1, I end up with a path that has a cost less than 30. So even though my first choice was not the most efficient one, in the end, I end up with a better path. So just picking the minimal edge is not going to work. What do we do? Well, this is a technique that is also present in Olympiad problems, where you use induction and you attempt to find a recursive formula. So label by alpha k and beta k, the shortest paths to AK and BK. And now we simply calculate alpha k plus 1 and beta k plus 1, knowing alpha k and beta k. And the formula is the following. Alpha k plus 1 is the minimum between alpha k plus the edge cost of AK plus 1 and beta k plus the edge cost of BK plus 1. And this is because in order to reach AK plus 1, we either reach it through AK or we reach it through BK. And we already know, we solved the steps AK and BK. So obviously the same holds for beta k plus 1. And if we look at the number of steps, at each step we're going to do 4 checks. We have 2 for alpha k plus 1 and 2 for beta k plus 1. So in total we do about 4n steps. So even for n is 100, it's still less than 1 millisecond. And that's pretty good. As a general idea, we should avoid exponential algorithms because they increase in time very fast relative to the input. So as we've seen, 2 to the power of 100 is really huge, whereas 4 multiplied by 100 is still small. However, what we've seen earlier only applies to this particular graph. How do we solve the general case? Well, there is this algorithm known as DIJKSTRA'S algorithm, and it works on a similar idea. if we look at the vertex, we label by T of V the current known shortest path for each vertex V. And by known, we mean that it has already been calculated in a previous induction step. Now, initially, for the source, it's going to be 0, of course, because the start is, there is no path. And for every other vertex, this initial T will be plus infinity, because we don't know any path yet. And now, at the induction step, we're going to have a current vertex, and we're going to look at its not visited neighbors. By visited, I mean that any vertex that was current at some point is labeled as visited and never looked at again. So we only look at the non-visited neighbors. And the idea is the same. We try to reach the neighbor through the current vertex. So we need to compare its current t-value, the current t-value of the neighbor, with the t-value of the current vertex, to which we add the edge cost between the current vertex and the neighbor. And now we pick the smallest of these values. If the neighbor's t-value is still the smallest, then we don't change anything. But if the t-value of the current vertex plus the edge cost is smaller, then we replace the t-value of the neighbor. And now we repeat this for all the non-visited neighbors. And for the next induction step, we pick the not visited neighbor which has minimal t. And this is going to work. We're not going to prove that it's going to work, but this is the idea. It is very similar to the previous step, except that we don't have a very clear hierarchy of the vertices, where we had them earlier with alpha k, beta k. Instead, here is a more general graph. I will also mention here the A-star algorithm, which is an extension of Dijkstra, and this is what we're going to use in the next section. The idea is to try to guess the shortest path based on some estimate that we know outside of the graph structure. For example, we can use the Euclidean distance as an estimate. And to give an example, more practical one, let's say you want to go to the store. Like, sure, you have to follow the roads, but you're not going to move in an opposite direction unless there is obviously no road through there. So you still have a general idea of where you want to go. So that's the idea behind the A-star algorithm. We look at the Euclidean distance from any vertex to the endpoint, to the destination, and we label it by d. And then instead of using the cost, we use a modified cost, where the new cost is the sum of the old cost, which we adjust by the difference of the d's between y and x. And when we use this cost at the midpoints of the algorithm, so in the middle, we might not have the most accurate results, but at the end, it's going to be accurate, because when we put the endpoint into d, the distance between the endpoint and itself is 0. So at the end, we're going to be fine. In the second part, we will talk about DELAUNay triangulations. First of all, what's a triangulation? Let's start with a set of points in the plane in general position. We can assume this without loss of generality. So, what is a triangulation of S? It's a set of triangles such that the vertices of the triangles are exactly the points of S. The triangles cover the convex hull of S, and any two triangles are either disjoint or their intersection is exactly a vertex, which is a point in S, or their intersection is exactly an edge. In these pictures, you can see examples of triangulations. What can we notice if we look a bit closer? Each of these triangulations has exactly 7 triangles and 13 edges. And the second one looks a bit more natural, because the first one has some long and narrow triangles. Neither of these are coincidences, as we will see. Let's look at the number of triangles and edges. If we have n points in S and k points on the convex hull, then the number of edges in any triangulation is 3n minus k minus 3. and the number of triangles is 2n minus k minus 2. How do we prove that? Let's label the number of edges by E and the number of triangles by T. And then we notice that a triangulation generates a planar graph with t plus 1 faces, the t triangles and the unbounded face. Now we do a double counting. We count the number of incidences of edge face in two ways. First, each edge is incident to exactly two faces, so that number is 2e. Then we look how the faces are, because there are exactly t triangles, which has exactly 3 edges, which have exactly 3 edges each, and the unbounded face has exactly k edges, so that number is 3t plus k. We also recall Euler's theorem, which gives us a relation between the number of points, the number of edges, and the number of faces. And now we combine all of the above, and we're going to get the desired result. Moving forward to the next point, we should try to avoid long, narrow triangles, such as the one highlighted in the picture. Why? First, aesthetical reasons, but that's not really a scientific argument, is it? There are also computational errors which might occur if the angles are small. So we should try to avoid these. And how do we do that? We introduce the concept of DELAUNay triangulations. A DELAUNay triangulation has the following property. For any triangle, the circumcircle of that triangle does not contain any other points inside of it. An example is in the picture where some of the circumcircles have been drawn. In the following section, we will prove that the DELAUNay triangulations always exists. It is also unique. And we will also see that the DELAUNay triangulation maximizes the smallest angle among all triangles. So it does the best job at avoiding the long and narrow triangles that were mentioned. Now it is time to prove the existence of DELAUNay triangulations. If we look at it without the terms, we have the following combinatorial geometry problem. We have a set of points S in the plane in general position, and we want to prove that there is a triangulation of S such that for any triangle, the circumcircle of that triangle does not contain points inside of it. This is a hard combinatorial geometry problem. In fact, I think it would be suitable, difficulty-wise, as an IMO hard problem. Of course, it is well known, so that disqualifies it. How do we approach the proof? There are 3 main steps that we need to fulfill. First is to solve the convex quadrilateral case with a flip, introduce the concept of a flip. Then, in the general case, we will repeatedly apply flips until it is no longer possible, and we will prove that the sequence of flips actually terminates. And the final step is to prove that the end result of that sequence of flips is indeed a DELAUNay triangulation. So the first step is about flips. They are called LAWSON flips. So in a convex quadrilateral ABCD, which is not cyclic because the points are assumed to be in general position, we can assume without loss of generality the following angle inequality. The sum of angles A and C is larger than 180 degrees, and the sum of angles B and D is smaller than 180 degrees. Then, using geometry facts, we can conclude that D and B lie outside the circumcircles of triangles ABC and ADC, whereas points A and C lie inside the circumcircles of BCD and BAD. So, if BD is the wrong diagonal, because the triangulation as indicated in the left picture, if we look at triangle ABD and its circumcircle, C is inside of it. This is due to the angle inequality earlier. Then we flip the diagonal, and instead of looking at BD, we look at AC, and again, using the earlier facts, we note that D is outside the circumcircle. So the result, in this case, for the convex quadrilateral, is a good triangulation. And the operation of swapping the diagonals is called a flip. In the second step, we will consider the general case, and we will try to apply a flip whenever possible. The idea is to prove that this sequence eventually terminates, and we need to prove this. In fact, I will show you two proofs. The first involves the lifting map. This assigns to each point on the plane a point on the vertical paraboloid given by the formula. X and y goes to x, y, and x squared plus y squared. Now, why do we use such a map? It has the following property or properties. A circle is going to be mapped into a plane. Well, in fact, it's going to be mapped to the intersection between a plane and the vertical paraboloid. A point inside the circle is going to be mapped to a point below that plane, and the point outside the circle is going to be mapped to a point above the plane. How do we prove this? It's just writing some equations. If we write the equation of the circle, and then we substitute x squared plus y squared to z, then we obtain a linear equation in x, y, and z, which is a plane equation. So that's why the circle maps into points which lie on the same plane. And finally, if we replace the equal sign by strictly less or strictly greater, we're going to get inside and outside the circle and below and above the plane. So that's how we prove it. Now, if we take 4 points, A, B, C, D, we label their images by A prime, B prime, C prime, D prime. Note that A prime, B prime, C prime, D prime is a tetrahedron, and it is not a plane because the 4 initial points are not on the same circle. So it is in fact a solid. It has a strictly positive volume. If we are in the wrong scenario, where C lies inside the circumcircle, this means that the 2 top triangles will be selected because of the reasoning earlier. Let's do the flip. If we swap BD with AC, then we also swap the 2 triangles, and now the 2 bottom triangles are selected. So by selected, I mean the triangles which correspond to triangles in the triangulation. So now what we want to do is to notice that A prime C prime in the first case lies below the roof, if we look at it from that perspective. Now we try to look at the volume of the whole figure. By more specifically, for each triangle, we're going to look at the volume between that triangle and its image. Then we sum this over all the triangles. And because we, in a way, lower the figure, the volume decreases after each flip. In fact, it decreases exactly with the volume of A prime, B prime, C prime, D prime, because we simply remove that tetrahedron from the figure. So the volume decreases and decreases strictly. So this means that at some point we will have to stop, because the number of configurations or the number of triangulations is finite. The second idea is to use sorted angles. So because we already proven that each triangulation has the same number of triangles, we can look at all the angles of these triangles and put them in a vector and sort them in ascending order. This means that each of these vectors is going to have the same length. Now we compare these vectors lexicographically, meaning that we look for 2 vectors, we look at the first index where they have different elements. Such an index exists because we're looking at different vectors, and now we give the same relation between the vectors as between the elements of that index. So let's say vectors v and w, and I is the index. If vi is less than wi, then v is less than w, and similarly for greater. And what we will prove is that after a flip, the new vector is larger in this sense. Let's consider again the quadrilateral and label the angles as in the picture. So we have A1, A2, B1, B2, C1, C2, and D1, D2. Note that in the picture They are marked with one line and two lines, but this does not mean that they are equal. It is just for more clarity. We also assume that BD is the wrong diagonal and AC is the correct one. So the old angles, meaning before the flip, are A, C, B1, B2, and D1, D2. Of course, by A and C, I labeled A1 plus A2 and C1 plus C2, as they are the initial angles of the quadrilateral. The new angles will be B, D, A1, A2, C1, C2, because we flipped BD to AC. So what we want to prove is that the minimal angle increases after the flip. And in order to do this, we're simply going to prove that each of the new angles is strictly larger than one of the old angles. This means that also the minimal angle from the new ones is strictly larger than some old angle, meaning that it is also strictly larger than the minimal old angle. Because C lies inside the circumcircle of ABD, if we look at arc AB, we will get that C1 is strictly greater than D2, because otherwise C would lie on the circle or outside the circle. Similarly, C2 is greater than B1. Also similarly, A1 is greater than B2 and A2 is greater than D1. So far we managed to solve the lowercase letters. Now the last part is easy. B is strictly greater than B1 and D is strictly greater than D1 because both B1 is contained in angle B and D1 is contained in angle D. So indeed we did prove that each of the new angles is strictly greater than one of the old angles. This means that the minimal angle increases. So this is what we wanted to prove. Now, when we look at the general case, when we do a flip, the only angles that are changed are the angles inside the quadrilateral, so the ones that were mentioned in the previous statement. So among these angles, the minimal angle increased. So now if we look at the vector, this is going to mean that the new vector is larger from a lexicographic point of view, simply because we look at where the minimal angle appears in the old vector, and then we simply see what happens. Because the vector is sorted, all the other old angles will appear to the right of the minimal angle, and because we increase that, even after the sort, we cannot obtain a smaller vector lexicographically. What's the conclusion? In both of these scenarios, we managed to find something that strictly increases or strictly decreases. So again, because there is a finite number of triangulations, eventually we won't be able to do any more flips. We cannot have an infinite set of flips, because this would mean that the sequence of either volumes or vectors would be infinite, but that is a contradiction. In fact, no edge will be flipped twice. We didn't prove this, but this is also true, so I thought I should mention it. This means that there are at most n multiplied by n minus 1 over 2 flips. In the third and final step, we need to prove that the configuration that we obtain after a sequence of flips that stopped is indeed a DELAUNay triangulation. We're going to prove by contradiction. So let's assume, for the sake of contradiction, that there is a point P which lies inside some circumcircle of a triangle delta. And then we consider E as the splitting edge, meaning that P and the other vertex of the triangle lie on opposite half planes in respect to E. And now we select among all these pairs of P and E the one with minimal distance. In the drawing, E is AC and ABC is the initial delta. So the distance between P and AC is Px. Now if we look at edge AC, there must be another triangle which has AC as an edge. Let's call that triangle DAC. First of all, D and B have to lie on opposite sides of line AC, because otherwise the triangles would self-intersect. So that's not good. Also, ABCD cannot be flipped, because otherwise we can do another flip, so the sequence of flips was not in fact terminated. This means that D does not lie inside the circle ABC. And now all we need to do is look at the configuration. Both X and Y, where by Y I labeled the projection of P on CD, so PY is the distance between P and CD. So X and Y lie on the circle of diameter CP. So if we want to compare PY with PX, we can also compare the angles PCD and PCA, and PCD is clearly smaller. So PY is less than PX. And this is a contradiction because we picked the pair P and E with minimal distance. So then we should have picked triangle ACD and angle endpoint P. So this is a contradiction. This means that in fact there is no such point P. So the end result is indeed a DELAUNay triangulation. And with this we finish the second part, which is about DELAUNay triangulations. In the next part we're going to put it all together. The first thing that comes to mind when we try to put it all together is that we were supposed to avoid certain polygons. That was the idea. Those polygons were standing for obstacles. So how do we maintain the configuration of those polygons? Because if we only look at the points, then the triangulation might end up destroying the polygons. The answer is to use the edges of the polygons as edges in the triangulation. And those, we simply fix them and we don't change them. We don't apply flips to them or anything. Now, of course, this result will no longer be a DELAUNay triangulation. However, using a similar argument as at the start, we obtain what is called a constrained DELAUNay triangulation. And the idea is that such a triangulation is good enough, because we're not looking for the absolute best. We are looking for a good enough solution such that the requirements are also true, and we can work with that. So let's see it in practice. Here is a drawing where we need to reach point E from point S, so from start to end, and we need to avoid the red polygons. First, we apply a constrained DELAUNay triangulation, and it's already in the picture. The idea is to try to keep the DELAUNay property as much as possible. Of course, in some areas it's not gonna work, but to try to get as good result as we can. Now, we consider the triangle graph, meaning the graph that has the triangles as vertices, and two triangles are connected if they share an edge. Now, the edge cost can be the distance between the centroids of the triangles, and this is what we're going to use. Then we apply, as in part 1, the A* algorithm, and we will find the shortest path in the triangle graph, and this is highlighted in green. So again, because now we're working with triangles, we find a path consisting of triangles. How do we convert this to an actual geometric path? Because this is a triangle path, but it is not a collection of lines that goes from S and reaches E. First idea is to connect midpoints of edges. This is gonna work because at every two midpoints, when we connect them, that's a midline in a triangle. So this means that it lies inside the triangle. And this means that we will always be inside triangles, which were selected in the shortest path. So it is a valid geometric path, but it is not an optimal path, because as we can see, especially in the top left, we take a very long corner when we could take a much better solution. So this is not an optimal path, but it is the first idea to construct an actual geometric path. There are multiple solutions to this problem depending on the scenario and depending on what is desired, because sometimes, for example, you can cross the polygons. Other times you worry more about performance and calculation time. So it depends. It also depends of the actual geometric configuration, especially if you have more information about the underlying structure. We're going to talk about the funnel algorithm as an example of how to smooth this path and make it better. It works like this in very short terms. We start with two colored edges. One is red, one is blue, and at the start they are the two edges adjacent to the starting point. And the idea is that we move further and further on the path by picking vertices, such that the angle between them becomes narrower. At some point, we're not going to be able to do that. So we either have to increase the angle or we would have to cross the colored edges. Like in drawing number 3, if we move the red edge, we're going to increase the angle. And if we move the blue edge instead, which is not drawn, we would cross the edges. And neither of these operations is good. So then we stop, we add that point, and we put it in the good path. And then we update the colored edges. Instead of starting from the previous point, they start from this point, and we go back to point 1. And because we added this point to the path, this is how we build the whole path. In the end, we get a nice result, which is a good path. It's probably the shortest. Where can we go further? There are some interesting topics to think about. The first is about avoidance. If we have multiple agents moving, usually they're labeled agents, they need to avoid each other. They might need to avoid each other. So how do we do that? It's not something that we will talk about, but it's something interesting to think about. There are some ideas about this. For example, the reciprocal velocity way. And this is a difficult topic. Second, even though my example started with a video game, there are some real-world applications to this. For example, we can use the same ideas in a warehouse or a factory, because you know the geometry, and even though in a warehouse you might need to consider the avoidance as well, there are fixed points where you need to move, and all the obstacles are placed in set places. So you might be able to come up with some rules, and then what you need to do is to find the shortest path between various destinations. So once again, this has actual applications, and there is a various skill set needed in order to deliver this from start to finish. As you've seen, we went into some theoretical combinatorial geometry proof for the DELAUNay triangulations. We also dabbled a bit in computer science and talked about algorithms and their efficiency. And of course, there are the logistical challenges to figure out how the geometry looks and how to use real-world data when calculating such things. And there is the actual programming to be done. So a lot of work, but in the end, it is something nice, and it does show how all these sciences blend together and create a real thing that helps. Thank you for watching, and to the contestants, I wish you good luck.